Hey there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we talked about the intermediate value theorem. We talked about the hypotheses, what the theorem says, and the main application of it, which is locating roots within a given interval. In this video, we're going to begin to get into theorems that rely on differentiability and continuity. We're going to start to look at why differentiability matters so much. Now, the main theorem that really relies on differentiability is the mean value theorem. But before we get into the mean value theorem, we're going to talk about another theorem first. And we're going to use this theorem once we talk about it to actually prove the mean value theorem. This other theorem is called Rolle's theorem, and here's what Rolle's theorem says. It says, let f of x be continuous on the closed and bounded interval a comma b, and differentiable on the open interval a comma b. So we're not including the endpoints here. The function does not have to be differentiable at the endpoints themselves. If f of a is equal to f of b, then there exists a c value strictly between a and b, such that f prime of c is equal to 0. So again, a function f of x, continuous on the closed and bounded interval, differentiable on the open interval. If you take those endpoints, you plug them both into f and you get the same thing out, then you know that there has to be some c value between a and b such that f prime of c is equal to 0. Or you know that there's a stationary point of f of x between a and b. And as I said, we're going to use this theorem to prove the mean value theorem. Now, the mean value theorem, as we said it before, is probably one of the most important theorems, if not the most important theorem in all of Calculus 1. If you go on to study higher level math and you see what's going on behind the scenes with all of these calculus facts that we just use for granted at this point, they all have this mean value theorem going on behind them. So this is a really, really big player, really, really key thing here. And this is what the mean value theorem says. Let f of x be continuous on the closed and bounded interval a comma b, and differentiable on the open interval a comma b. Then there exists some c value between a and b, such that f prime of c is equal to f of b minus f of a all over b minus a. And what we're going to do is we're going to look at a little visual as far as what this mean value theorem, or MVT for short, is saying. So I've drawn a function here. The function is in purple. I labeled a couple points, a comma f of a and b comma f of b. I have drawn a green dashed line between those 2 points. What that green dashed line is it is the secant line that goes through those 2 points. The slope of that line is the average rate of change. For short, AROC. And the average rate of change of a function over an interval is the difference in the y values divided by the difference in the x values. The average rate of change of this function over this interval a comma b is f of b minus f of a over b minus a. Now, f prime of c, thinking all the way back to chapter 1, we learned that f prime of a is the instantaneous rate of change of f of x at x is equal to a. but it's also the slope of the line tangent to the curve at A. So f prime of C here if I call this my tangent line L of x, then the slope of this line is going to be f prime of C. And what the mean value theorem says is that if your function is continuous on the closed and bounded interval, and if it's differentiable on the open interval, then there is some c value between your endpoints. There's some c value between a and b, such that the average rate of change of the function over the entire interval is equal to the slope of the line tangent to the curve at one particular x value, specifically x is equal to c in that interval. So the tangent line and the secant line are going to be parallel to each other. This is just a visual of what the MVT is saying. This is a geometric or graphical meaning of the mean value theorem. But now we're going to get into the actual proof of the mean value theorem. We're going to see how we get this result. And it's not too bad. It's fairly low level for a Calculus 1 type theorem. So I feel that we can go through this proof and it shouldn't be too much trouble. So we start off by assuming our hypotheses. We're assuming that f of x is continuous on a closed and bounded interval and is differentiable on the open interval. Now what we're going to do to help us get to the end result that we want is we're going to create a new function that involves this function f of x that we have here. This is a fairly common kind of thing that gets used. It may not seem like it's valid, yet it is. So I'm going to define this new function g of x. I'm going to call it f of x minus f of a minus f of b minus f of a over b minus a, that whole big constant, times the quantity x minus a. Now, because f of x was continuous on this closed and bounded interval and differentiable on this open interval, and we took combinations of f of x and other polynomials, which are continuous and differentiable everywhere, g of x is also going to be continuous on a comma b, closed interval a comma b, and differentiable on the open interval as well. Now we're going to take the two endpoints, a and b, and we're going to plug each of these guys into g of x, and we're going to see what we get. Well, if we plug b in, we are going to get f of b minus f of a minus f of b minus f of a over b minus a times b minus a. Well, if we look at this as one group of terms, the b minus a's cancel out, and now we're taking a quantity and we're subtracting it from itself, so that gets us 0. If I take a and plug it in for x, I get f of a minus f of a, which is 0. And then I get some constant c times a minus a, which is 0. 0 minus some constant times 0 is going to be 0 as well. So I note that when I plug when I find g of a and g of b, I get the same thing. Well, a function that's continuous on the closed and bounded interval, function is differentiable on the open interval, and taking each of the endpoints of the interval and plugging them into G gives me the same thing. All these guys satisfy the hypotheses of Rolle's theorem. So this is why we say we use Rolle's theorem to prove the MVT, the mean value theorem. So by Rolle's theorem, there exists some C value between A and B such that G prime of C is equal to 0. Now, if we just go back to the statement of G of X, we need to differentiate G of X and then plug in C. Well, if I differentiate G of X here, the derivative of f of X is just f prime of X. Minus f of A. This is just a constant, so when I differentiate it, that's going to give me 0. This right here is just some constant, so I have some constant times the quantity x minus A. I could multiply that constant in, and then when I differentiate, I'm just going to be left with this constant here. So G prime of X is going to be f prime of X minus the quantity f of B minus f of A over B minus A. And we see that when we plug C in, we get G prime of C is equal to f prime of C minus f of B minus f of A all over B minus A. And by Rolle's theorem, this quantity right here is equal to 0. So we set that equal to 0, we move the fraction onto the other side, and we come up with the conclusion of the mean value theorem. So this is the proof of the mean value theorem. Now, I'm not going to ask you to regurgitate this proof back at me, but you should have been able to follow with what we were doing throughout this proof. You should have been able to follow through each step and just understand why we can say the next thing that we said. So this is the end of our video here on Rolle's theorem, as well as the statement and the proof of the mean value theorem. In the next video, we're going to do several mean value theorem problems. And we're going to see what process you have to go through to solve those kinds of problems. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.